The topic of lesson 9 is the definite integral, and the integration can be seen in many ways as the inverse operation to differentiation. And in the first few slides of these lessons, I want to just go over the basic idea how integration is defined as a limit process, and then go over a few problems from the book. I think here it's really important that we get as much practice as possible before we move on to the next lesson, where we then formally deal with this limit process. So let's start with the very basics. Suppose you want to drive 150 miles in your car. So let's say you're on a highway and there is some landmark that you don't want to miss, and there are no mileage markers along the way, and also your odometer is broken, and also you have no phone with you or no GPS, nothing. However, your speedometer works, so you can, while you cannot directly see how far you've driven because your odometer is broken, you can see at any moment how fast you're driving. And let's also assume, to make things a little bit easier, that your cruise control works. So cruise control, okay. Now in that case, there is a solution to this problem, assuming that the highway is rather empty and there's no traffic whatsoever. So in that case, you would just set your cruise control to 60 miles per hour and drive for 2.5 hours. Because if we constantly drive 60 miles per hour, then we would drive 120 miles in the first 2 hours and 30 miles in the additional half hour. So altogether we would drive 150 miles. Let's illustrate this graphically. So here we have our velocity graph, right? So that's the velocity function. The blue function is the velocity function, right? And here t, this is the time axis. The x-axis is time, y-axis is velocity, right? And now we're driving, using our cruise control, we drive 60 miles an hour all the time, right? So then after 2.5 hours, right, we'll have driven 150 miles exactly. You can also interpret this as an area here, namely, if you look at the area of that rectangle, right, of that red rectangle, right, so the area would be, right, 2.5 times 60, which is 150. And together, these two things already give us the very basic ideas of integration. So integration has something to do with inverting the process of differentiation, and it also has to do with something with areas under curves. This is a very simple case here, so it will get quite more complicated than that, but it is a good starting point. So the idea was that we've seen that velocity is the derivative of the distance function, right? Remember when we talked about derivatives, that was one of the really standard examples, right? If we take the derivative of distance, right, of the distance function, the instantaneous rate of change of distance gives us velocity. Now our problem is somehow the inverse, right? So we don't have the distance function, right? Our odometer is broken. We only have velocity, how a speedometer works, right? Now, how can we get from velocity back to distance, right? And in this setup that I made in the original problem, this was very easy, right? Because we could use our cruise control. Right? We'll see in a moment what we do if we don't have cruise control at all, right? But in this basic setting, we just said, okay, we just use our cruise control to make sure, and then say, okay, we need to drive the exact amount of time to get the exact distance that we want. But the way we interpreted it here was actually just taking the area under the velocity function, right, to get our distance function back. Now, how would we tackle the same problem if there were no cruise control, or there were a lot of traffic, right? So we'd have to stop very often, or slow down, and then we can accelerate again, and so on. So the solution that that we found in the first part only worked, of course, if we can drive constant speed for a long time, right? In these cases, we cannot really do that either, because we cannot really keep our foot on the gas pedal in a nice constant way, or even worse, if there's a lot of traffic, so the circumstances prevent us from doing that anyway. So in this case, our velocity function might look something like this, right? So we can accelerate, we have to slow down, then we can stay at a rather good speed for quite a while, but then we hit a traffic jam, have to slow down for a bit before we can continue at a much lower speed, because traffic is much more dense now, for example, right? So you can think of many different situations, many different velocity curves that you could obtain depending on your driving situation. What I want to say is, however, right, so it might not be always that nice that we can just use the cruise control to solve our distance problem, so to say. The question now is, even if we have to drive the way that traffic dictates, can we still solve our problem that says that after 150 miles I want to stop and look at that landmark, right? It might be a hidden landmark, of course. If it's something very famous and tall, then there's no sense in calculating here. We just stop when we see it. But let's assume it's a very small thing you just don't want to pass along the highway. Okay. Is there a mathematical way we can still do this? And indeed, there is something we can do. So assume you're not alone in your car. You have another passenger, and what you could do would be, well, in reasonably short intervals, you could read the current speed from the speedometer and say, okay, and these intervals have to be somehow regular. Let's say every 5 minutes, right, we read the speed, right, from the speedometer. So read the speed every 5 minutes. This will give you measure points v1, so the velocity after the first 5 minutes, v2, velocity after the second 5 minutes, v3, velocity at 15 minutes drive, and so on, right? So, and your passenger records these. So he or she keeps a sheet and notes all of these measured speeds, right? And then you compute the following sum, right? You take 1/12 times v1. So why 1/12? Well, our unit here are hours, right, as we used before. And 5 minutes is a 12th of an hour, right? 12 times 5 is 60. Right? So, and v1 is the speed that you have driven after 5 minutes in 5 minutes, right? So that's the first measuring point you took here, right? So that's intended to be an approximation of the speed that you've driven over the first 5 minutes, right? So if you drive speed v1, right, constantly over 5 minutes, then after 5 minutes, right, since this v1 is in miles per hour, right, miles per hour, right, and we have minutes here, 5 minutes, so we have to, if we drove this v1 for an hour, we would drive v1 miles, right? But we only drive it for 5 minutes, so that's why we have to multiply by 1/12. So this would be an approximation of the distance driven in the first 5 minutes, right? So approximation of distance in first 5 minutes. Right? So likewise, this here would be an approximation of the distance driven in the next 5 minutes, right? Because it's our second measuring point, v2, right? So it would be here. And likewise, this would be an approximation of the distance driven in the next 5 minutes. So in total, we would get here an approximation, so these three terms together would give us an approximation of the distance driven in the first 15 minutes. So altogether, first 15 minutes. And it takes into account that our speed changes over the course of 15 minutes, right? So we are slower at the beginning, faster at the end of the first 15 minutes, right? That's why it's more accurate than just taking one measuring point after 15 minutes. Okay. So, and what you and your co-pilot could do now is just keep doing this until this sum, right, is close or to or exceeds 150 miles. Right? Then you know that you're approximately driven 150 miles. Of course, it is only an approximation, so we cannot have this complete precision anymore that we had when we could use the cruise control and just set it constantly to 60 miles an hour, and then the speed would be constant. Here the speed is not constant, right? So we make a little bit of an error, right? Because we assume that v1 is the approximation, right, for the speed driven during the first 5 minutes, but during the first 5 minutes the speed still varies, right? So if you wanted to make sure that you're very close to get very close to the actual distance driven, you would kind of decrease the intervals in which you read the speed, take the measurements from 5 minutes to 1 minute to half a minute to even every 10 seconds, right? That would be very, very precise. And do the same thing, of course, now if you decrease it from 5 minutes to 1 minute, then you would have to replace 1/12 here by 1/60th, right? Because 1 minute is a 60th of an hour. And just as before, we can do the whole thing graphically, or give a geometric interpretation of what we've been doing using the graph here, right? So here are our intervals, right? They're equally spaced. Of course, they are not perfectly equally spaced because I can draw them this way. But they are, let's assume they're equally spaced, and then we take the measuring points, right? So we take velocity driven after 5 minutes, so this would be v1, right? And then velocity driven after 10 minutes, right? That would be v2. And velocity driven after 15 minutes, that would be v3, and so on. And what we do now, so let me zoom in a bit. So what we're doing here is the following, right? So we take these measurements and then we compute the area of those little columns here, right? Because what is the area of this column, or this rectangle? Well, it is 5 minutes, which is 1/12 of an hour, right? That's the length of this side, times v1, which is the length of this side. Right? And likewise, we take the area of this rectangle, right, which has, again, this little, here has length 1/12. This, the long side, has length v2, and so on. And then we take this one, this column rectangle, right? And that would be 1/12 times v3. And we sum the areas up of those three columns. And that gives us our approximation of the distance driven. And again, you see, there seems to be a connection between going from the derivative, that is in our case speed, to the original function, distance, and computing areas under a curve, because what you see here seems to be a pretty good approximation of the area that is given to us by taking the area between the curve and the x-axis, right? We overestimated a little bit, right? But not by much. And if we make our intervals here smaller and smaller, right? Let's say from 5 minutes down to 1 minute, down to half, 30 seconds down to 1 second or 10 seconds, right? You will see that those rectangles, those columns, will get narrower and narrower, but at the same time align better and better with the actual function. So here's the basic idea again. So we measure speed in regular intervals. That's important, right? And we used delta t, so that's the time interval that we use, right? 1/12, this would be 5 minutes. You could also use 1/60th, which would be every minute. 120th would be, right, every 30 seconds, and so on. And you get measuring points, right? The speed after 5 minutes, 10 minutes, or after if you use minutes, you would have to first minute, second minute, third minute, and so on. And then you compute this sum, delta t times v1 plus delta t times v2, and so on. You can also, of course, just sum, since we always multiply by delta t here, you can also write this as delta t times, and then you just sum up all the speed measures here, right? Okay. This is what is essentially called a Riemann sum. Riemann sum. And we've also seen that if you use smaller intervals, smaller and smaller intervals, you get a better and better approximation of your actual distance driven. Right. So the basic idea of the definite integral is use limits, right? Just as differentiation was the instantaneous rate of change, but it was defined as the limit of the average rate of change, where you made the interval smaller and smaller, right? Over which you take the average rate of change. Now you here make this interval smaller and smaller. So for the definite integral, you let delta t go to 0. That's the basic idea. What happens to this sum here if you let delta t go to 0? So let's apply these ideas to some problem from the book and practice these kind of problems also, because they're very similar problems on the quiz for this week. So here's the problem. Figure 5.11 shows the velocity v of an object in meters per second. So now we have meters per second instead of miles per hour, but it's no big deal. Estimate the total distance the object traveled between t equals 0 and t equals 6. So now we want to actually know how far did we drive or travel in the 6 seconds here. Right? So if we wanted to solve this, or if we apply the ideas that we developed before, what we would do is now just measure the speed after 1 second, 2 seconds, 3 seconds, and so on. So that would give us these points here after 1 second, 2 second, 3 second, 4 second, 5 seconds, and 6 seconds, right? And we would, what we could do is just now estimate the amount here, right? The speed. So it would be like 14. Then it would be about 20, right? Then it would be about 26, 30, and it would be, let's say, 34 and 38. So those are speed measuring points. And then we would form the accordant Riemann sum, right? So what is our delta t here in this case? Delta t, well, what is the interval width? Well, it's just 1, right? It's 1 second. Our units are second, right? Interval width is 1 second. Right, so we would just have to do delta t times the sum of all these, 14 plus 20 plus 26 plus 30 plus 34 plus 38. And now if we compute this, well, we'll obtain 162 meters. However, keep in mind that this will be not the exact distance driven, because what we do is, well, we essentially computed the area of these rectangles here, right, as before. And since they're always above the function, right, we overestimate the actual distance driven. We could also, so what we've done here is what we call in the book a right-hand sum, right? Because we always took the points on the right end of the interval, right? The values. We could also take a left-hand sum by just looking at the values at the left end of the intervals, and then we would get 0, 14, right? 20, 26, 30, right? And 34, right? So except for the first and the last part, right? Those are identical with the values in the right-hand sum, right? Because, well, we're using the same data point. It's only that in one case they are at the right end of the first interval. In the second case, they are at the left end of the second interval, right? And now if I form the Riemann sum with this, right? So we would have delta t times 0 plus 14 plus blah, blah, blah. So all these numbers up to 34, we would get 124. So using the left hand and the right hand sum, we would get that the distance traveled is between 124 and 162, right? So this here would correspond to these rectangles here, or these columns, and so on. Right? Okay, now if you look at the book solutions, it will tell you that it's estimated between 140 and 150. So how does the book get this solution? Well, I guess what is intended here is to use the additional structure, right, that is given by these squares. You see that each of these squares has an area of exactly 10, right, because it's 1 times 10, right? 1 times 10. Okay, so now you can just look at, okay, how much of the area is taken in by the curve, right? So for instance here, we would say we'd have, if we wanted to estimate this column, right? So that would be area 30 plus something, and now this something you could just estimate by looking at how much does this square take of the whole square, which is area 10, so of this whole square here, and you would say that's maybe a fourth or something, so you could say like 30 plus 2.5. For instance, right? So, or even like 30 plus 2 or so. And then you take those sums and you would get probably a closer estimate. So try it yourself what you can do geometrically here. However, in the quiz, the values that are given for you as a choice, they should be so clearly right or wrong, so within the reasonable approximation and just being a totally unreasonable approximation that you should not have a problem with estimating here. Okay. So in the previous problem we did the estimate using the graph of a function. Now we're just using it, doing the estimate using a table, because if you recall, all we needed to do our estimates were certain measuring points, right? Certain data that were measured the speed at specific regular intervals. So here is so this is 5.1 number 8, right? Roger runs a marathon. His friend Jerry rides behind him on a bicycle and clocks his speed every 15 minutes. So now we have 15 minutes instead of every 5 minutes that we did in our first example. Roger starts out strong, but after an hour and a half he's so exhausted he has to stop. Jeff's data follow. So here's the table with the data that Jeff measured. Now, question A, assuming that Roger's speed is never increasing, give upper and lower estimates for the distance Roger ran during the first half hour. So what does it mean now to give upper and lower estimates? Well, we use a left and a right hand sum. It's just the question which is the upper and which is the lower estimate. Well, the idea is here the speed is never increasing, right? So that will mean that his speed function will look something like this. So he starts out strong at 12, then it drops to 11, drops to 10, and so on, right, in miles per hour, right? So now if we take a left-hand sum, right, that would mean our first data point would be at 0, right? And then this next data point for the first half hour would be at 15, right? So we would do this, right? First data point at 0, next data point at 15, and we would compute this. So since the speed is always decreasing, right, we would get a clear overestimate. So the overestimate in this case is the left sum, right? So this is for part A. Part B is similar, of course, is 1/4 times 12 plus 11. Remember, 1/4 is just, since our units are miles per hour, and 15 minutes is a quarter of an hour, so that's why it's 1/4 here. So 1/4 times 12 plus 11, so that would be 5.75 miles. Now the lower estimate, right, would be the right-hand sum, because we would take this as the first data point. And then this would be our next data point. The right-hand sum would be the underestimate. And that would be 1/4 times, now we'd have 11 plus 10, right, which would be 5.25 miles. So in part B, we would do exactly the same thing, now only we do the full estimate over the entire hour and a half. Right. Again, the overestimate would be the left sum. And of course, this is only because the speed is always decreasing, never increasing, right? So that means that the left data point is always higher than all the other data points that follow, because the speed is decreasing, right? That's why it's an overestimate. If his speed were increasing in turn, the left sum would be an underestimate, right? Like we had in problem number 7, right? If you recall, there we had an increasing function. There, the left sum was an underestimate. So you should go back from maybe and compare. Okay, now again, our data points are, intervals are 1/4, right? 15 minutes of is 1/4 of an hour, and then we just sum up everything starting at 0, right? Because we're taking the left sum. We would take this, 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 and this. 12 plus 11 plus 10 plus 10 plus 8 plus 7. And if we sum all this up and divide it by 4, we get 14.5 miles. And similarly, the underestimate would now be the right sum, and that's equal to now 1/4 times 11 plus 10 plus 10 plus 8 plus 7 plus 0. Right, and you see already it will definitely be an underestimate, because you have this data point 0 here, right? Although that he only it's 0 because that's when he actually stops after 90 minutes, but it does not mean that his speed was 0 the whole last 15 minutes that he ran, of course, right? But now if we can calculate this, and we get an underestimate of 11.5 miles. So in the previous examples we actually approximated, so we estimated the exact distance traveled. In this problem here, that's 5.1 number 11, we'll actually be able to compute it exactly. And the reason why we can do this is geometry. So in the previous examples, the speed varied quite a bit, right? So it was decreasing, increasing, and so on. Here it's increasing, but it's increasing at a very steady rate, right? Namely at a constant rate. Okay, So, and that enables us to use geometry to compute the exact distance, right? So I'll draw the graph, because the basic idea we can get even without plotting an exact graph. So here we would have t, and then again on the y-axis we have v, velocity, right? And then we have a velocity function is 5t, so that's a line with slope 5 through the origin. Right. So and we want to measure the total distance that is traveled in the first 10 seconds, right? So let's assume here we have 10, right? Then the value here would be, the coordinate value would be 50. Right. Okay, so what is the exact distance? If you recall how we did this before, well, before in those examples, we started out with a graph and some velocity function, right? Let's assume it looked like this. And then we try to approximate by using data points, measuring points, right, in regular intervals. And then we computed the area of the rectangles that is given, right? And we observe that if we make the intervals here smaller and smaller, we get a better and better estimate of the actual distance. So the actual distance then geometrically actually corresponds to the area under the curve during the interval that we are interested in. So in this case, the interval between 0 and 10. It is only because in those cases the actual area was geometrically very hard to measure that we had to resort to these approximations. Here, however, we see immediately that the area we're interested in is a triangle, is a very nice triangle. And we know geometrically how to compute areas of triangles, right? Because the area, so total distance is equal to area of triangle. Triangle, which is equal to, so well, what is the area of a triangle? It's, since this is a right triangle, it's just this, length of this side, times length of this side divided by 2. Right. So that would be 10 times 50 times 1/2. So roughly, so now we can not roughly, that is exactly, because we know it's 10, 500, 250. So in this case, where geometry is our friend, right, because we know triangles, we can compute areas, we can use this nice correspondence between computing integrals, right, and areas, the definite integral and the connection to the area under a curve. Because this curve is so nice and regular, we can use geometry to compute the area, right? So 250 meters is the distance. So in the following lessons, especially in lesson 10 and 11, we will learn ways how we can compute this area here, even if the graph is rather irregular, has a strange geometric shape, right? Not one that we know from elementary geometry, such as triangles, rectangles, and so on, right? But there are problems like this on the quiz. So, and if you here, you just have to remember exact distance. You can do it because this function is very regular, and the connection between the definite integral and the area under a curve, you can use geometry to compute this exactly. The next problem is about interpreting the interval and relating it to things like velocity and so on, distance, and especially comparing functions with respect to their interval. So this is 5.1 number 17. Two cars start at the same time and travel in the same direction along a straight road. The figure below gives the velocity v of each car as a function of time, right? As before, as we had in all the problems before. Which car attains the larger maximum velocity? Well, that's not hard to answer, right? Because we see here, this is the velocity function, right? So we are given the velocity function. This is the velocity function for A. This is the velocity function for B. Now this just asks which car attains the larger maximum velocity, right? So that means which car has the larger global maximum. And there we see, well, here we have the maximum for A. Here we have the maximum for B, right? Okay, so here clearly car A has the larger maximum velocity. The second question is, which car stops first? Well, now we see, well, this is the velocity function. A car stops, right? Stops means velocity equals 0. So where does the velocity of each car reach 0? Well, we would say, well, if we assume that we have a little bit of velocity here, so it moves very, very slowly, gets very, very fast, right, in the case of car A, then slows down rapidly and moves very slowly for a bit. But we would say here it stops because it reaches velocity 0, right? Velocity becomes value 0, whereas car B reaches velocity 0 over here. Okay, so again, car A is the one. It stops first. Car B goes a much longer time. So the third question now is, which car travels farther? Now we actually have to see, well, this is just the velocity function, right? Even though car A attains a higher maximum velocity and makes a lot more progress early on, it stops also much earlier, and car B goes on much longer, right? Now, how can we say which car travels farther? Well, we've learned that the distance can be recovered or interpreted as the area under the curve, right? Because it's the definite integral. So now we have to compare the area under the curve for car A, which would be this, with the area under the curve for car B, which would be this. And there it's easy to see that the blue area is much larger than the red area, right? So therefore, in this case, we have car B traveling farther. On the quiz, you have a similar problem. You'll see there's a similar problem where you have to interpret velocity curves in this in this sense here, right? So just keep in mind what you have are the velocity curves, not the distance curves, right? Here, right? Then you have to infer the distance function by looking at areas under the curve. So now we pass from these examples, they all use velocity, to the pure mathematical computation of definite integrals. We can't compute them exactly now. That's what we will learn next week when we do the fundamental theorem of calculus. However, we can still do the same ideas, apply the same ideas to any function, right? no matter whether it's a velocity function or not, because left-hand sums and right-hand sums are always defined. Okay, this is a problem from 5.2. Estimate the definite integral 0 to 6 2 to the x dx using a left-hand sum with n equals 2. So n equals 2 means the number of points, right? Number of data points. So in this case we have 2 data points. So the first thing that you do then is you look at your interval, right, which is 0 to 6, right, and you divide it evenly, right, so that you get 2 data points equally spaced, right. So in this case we would have to take the step width, so delta x would be 3, right, because we have 2 data points, a total length of 6, right. Everything equally spaced would have to be delta x equal to 3. So once you have done that, so first thing is establish delta x or delta t or whatever the name of your variable is. Once you have done that, now you go in and measure or take the function values at exactly these points that you're interested in now. So we have delta x equal to 3, and we are required to compute a left-hand sum, right? So our first data point would be the left end of our interval, right? So that's where we would start. So we would first compute f of 0, which is 2 to the 0, which is 1. And then we would have to compute the next data point at the f of 3, right, which is 2 to the 3rd, which is equal to 8. And then you would form the left-hand sum by just saying, okay, I have delta x times f of 0 plus f of 3, and that's 3 times 1 plus 8 is 9, so that would be 27. So if you wanted to compute now the right-hand sum too, well then of course your first data point would be f of 3 and your second data point would be f of 6, right? So the right-hand sum, the right sum would be delta x times f of 3 plus f of 6, which would be 3 times 8 plus 2 to the 6 is 64, so it would be 3 times 72, which is 216. So here you have a good example how the discrepancy between the left sum and the right sum can be enormous, right? Because the function grows extremely fast, so the overestimate and the underestimate differ extremely. So in this case you would see that in particular taking just 2 measured data points is way not enough to get an accurate picture of this. So it will be very interesting once we will be able to compute this exactly, right? What the actual value this compared to these, how big our error is there. So the last couple of problems, they're very similar to the quiz, to a kind of quiz problem. I just changed the numbers a little bit. So here you're asked again to use geometry to compute this definite integral. This is similar to the problem we did before, where we were asked to exactly compute the distance function, right? Now the only difference is that the geometry is just a little bit more complicated, but not much. So the idea is as follows. You draw the graph, right? Or just try picture it, and so you know what geometry you actually have to do here. So we have a graph that crosses the y-axis at 2, so has a y-intercept at 2, and then grows is the slope of 3, right? And we're asked to compute this interval between 0 and 2, right? So here would be 2, right? And we're asked to compute this integral, so that would be the same as this area here. And we see we can now split this into two sub-problems, namely compute the area of this rectangle here, right? Or in this case it's actually a square, plus the area of the triangle, right? So the area of the square is 2 by 2, right? We have a y-intercept at 2, so it would be 4. And here we would have the area of the triangle would be, again, one side length times the other side length. So here our function value at 2 would be 3 times 2 plus 2, so it would be 8. So this side length would be 6, right? And 2, so it would be 6 times 2 divided by 2. In other words, would be 6. So the total area then would be 6 plus 4, area of the triangle, plus area of the square here. So total area would be 10. I want to do one last problem similar to the previous one, but with an important difference. So far our analogy between definite integral and area under curve was perfect because we never had to face negative values. Right? But if you are, I'm sure, know by now from reading or the material or watching the videos, this goes only so far, namely as long as all your function values are positive. If there are negative function values, these will actually contribute negatively to the definite integral, right? So in particular, it will happen in the problems like this here, right, where we again are asked to use geometry to compute a definite integral. Again, it's a simple function, and that's why we can use geometry to compute it. But now something happens, namely, right, we graph the function a little bit. Right, so this is now a function that crosses the origin and has slope 1/2. Right? So here, between at -1 and you would have 3, right? We have negative values, right? So what we would have to do now is to compute this triangle and to compute the area of this triangle, but then not add them, but instead subtract the area of this one, of this little triangle, from the area of this triangle, because this is positive, right? So because there the function is above the x-axis, and here the function is negative, so that it will contribute negative values to the overall definite integral, right? So let's compute the areas. So we would have here, this would be, area would be equal to, well, side length times side length divided by 2. It would be 3 times So what is the other side length? Well, it's just the function value at 3, right? That would be 1/2 times 3, so it would be 3/2, right? And now we need to multiply the whole thing by 1/2, so it would be 9/4. And now the negative area, so that would be this one, right, would be, or the one area that we have to subtract would be, well, side length again would be 1 times, now this would be side length here, function value at -1 would be -1/2, but of course we're only interested in the side length here now, so it would be actually 1/2, and then multiply the whole thing by 1/2 because it's a triangle, right? Instead of, otherwise we would just get the area of the whole rectangle. Okay, so that would be 1/4. So the whole thing now would be the area of the triangle that is above the x-axis would be 9/4. And now subtract the area of the triangle that's below the x-axis would be 1/4. So that would be 8/4, which is 2. Yeah, so keep in mind that the area, or the analogy or connection between definite integral and area under a curve, right, is kind of imperfect. It works out very nicely as long as the function is positive. If there are, as soon as there are negative values, this does not work completely anymore. So then you have to actually kind of separate your function between the negative area and positive area. So there is a number of problems in section 3 that also addresses this. So please make sure you read through this. This is quite important. So I hope this helped you a little bit to understand the definite integral a little bit better. It is the other major concept of calculus. So we'll continue exploring that in the following 2 lessons.